Okay, this is the first of these screen recordings that I'm going to do. The plan is that in addition to the explanation videos that you saw with me in the studio, that I'll work through various problems on the screen as screen captures with audio. And the goal of those is to just give you a sense of how to solve particular kinds of problems, how to approach them, and so on. And I'll try and talk a little bit about why we solve problems the way we do and how we teach our students to solve problems in particular ways that are effective and that make them more likely to do well in tests and exams and so on. So this particular worksheet, the very first one, I've called setting up a problem, and I'm kind of thinking about the idea of making sure that we teach our students that when you attack a problem, don't just find a formula and plug in some numbers and hope for the best, but actually set the problem up in terms of actually figuring out what's going on physically. I think I mentioned this in the explanation videos as well. So we want to, at the very least, make a start with a diagram. I always say draw big diagrams and make them as clear as possible, label them, don't scrimp on the paper used. I'm going to slightly be a hypocrite on that point because I don't have a huge amount of space on these particular documents, but I'm going to try to at least draw some kind of diagram every time. I might not remember every time, or it might be so simple we don't need a diagram. So first thing I'm going to do is try to draw a little guy on a roof, and he's with his very long arm he's going to throw a ball downward. He's throwing it down off the roof, and we know that the time taken to reach the ground is 3.2 seconds. So the first thing we do is draw a diagram. Second thing we do is sum up what we already know and what we're wanting to know. So u, the initial velocity, is 0.8 meters per second. And I have to apologize for the handwriting. I'm doing this with a stylus on a tablet. Hopefully I'll improve with my skills as I go. What we want to know is the final velocity just before it reaches the ground. So obviously once it reaches the ground it will collide and come to rest or bounce or whatever it does. But what we don't know is how fast it's going just before it reaches the ground. What else do we know? We know that the acceleration is going to be 9.8 meters per second squared, because it's just accelerating due to gravity. But we should actually pick a direction for that. We can choose, remember, the motion is relative, we can choose upward or downward as our positive direction. Since it's already moving downward and it's going to accelerate downward, it probably makes sense to choose downward as positive. So let's choose down as our positive direction. So that means that 9.8 is positive rather than negative. It would be negative if he'd thrown it upward, for example, or if we'd just chosen upward as our positive direction and downward as negative. And what else do we know? We know that the time is 3.2 seconds to reach the ground. So t equals 3.2 seconds. Now it might be a little bit of a hassle for students to do this diagram and do the summary of information, but it means that they're going to approach a problem well, know what they want to know and what they do know. Now we have a series of equations of motion. We have v equals u plus at, we have s equals ut plus a half at squared, and we have v squared equals u squared plus 2as. Now of those three, we have a v, a u, an a, and a t in our thing, so we know it's pretty easy to choose which equation to use. So we're going to use v equals u plus a t. Now, in terms of actually what to do next, some people prefer to plug in the numbers and work with the numbers and solve that way. Some people prefer to rearrange the algebra with the equation all in pronumerals first and then find out and then plug in the numbers once you've rearranged. Sorry, lost my train of thought for a moment there. Okay, so I think what I'm going to do is the latter. I'm going to rearrange first. So what do we actually want to know? we want to know the velocity. Hang on, I've just waffled on for nothing because the velocity is already the subject of this equation. So we will leave it exactly as it is. So we'll put in the initial velocity, 0.8. Now, we could also add the units. I'm not going to here because I'm kind of running short on space. Quite often teachers will get students to add the units at every step, and it's a good way of getting them to remember the units and remember the way units cancel and the dimensional analysis, but it's also a massive pain to do, particularly with multi-line calculations and so on. So I tend to remind them what the units are, but not make them write them out for every step. Your mileage may vary on that one. So plus the acceleration, 9.8, times the time, 3.2. Now you would obviously lay it out in a little bit more detail than this, and I won't put that unit there. Okay, equals 0.8 plus 9.8 times 3.32 is 0.8 plus 3.14. I should probably say that I'm not doing these calculations in my head. I prepared them earlier, and that's probably good practice to actually go ahead and prepare them earlier, or ask a student with a calculator to calculate it. So the final velocity v is equal to 3.94, and remember to put the units, and remember to put the direction. So it's positive, and we decided downward was positive, so it must be a downward velocity. So in that case, it's a very simple calculation, but it was mainly about the idea of making sure that we laid out everything and used the correct steps. And as I say, this is a bit messy because I'm working with a big stylus on a small screen, but hopefully gives you a sense of what we're trying to do. And some of the calculations to come will be less straightforward than this one.